everyone, and welcome to the next session on vector-Oblivious linear evaluation, which will be given by Peter Scholl. Peter Scholl is an assistant professor in the cryptography and security group at Aarhus University in Denmark. He has worked extensively on bridging the theory of secure multi-party computation into practice with more efficient protocols and implementations. He began this line of work while doing his PhD with Nigel Smart in Bristol, where he worked largely on the SPIDS family of protocols for dishonest majority MPC. He's also known for his work on faster protocol for Oblivious transfer extension, and more recently on homomorphic secret sharing and pseudorandom correlation generators, which he's also going to talk here in this call. So we're very, very happy to have Peter here. Peter, the stage is yours.
Thank you very much, Kamid. I just want to say it's a great honor to be part of this school this year. Really happy to be here. So I'm going to talk about vector-oblivious linear evaluation. This is the first on 2 of these talks for today. Okay. So to start off with, just a quick overview of the 2 talks and how they connect with the rest of the school. So this talk now is going to be a kind of slightly more gentle introduction to vector-OLE and OLE, including some basic protocols and applications to motivate this core primitive. And then the second talk this afternoon will be focused on an application of vector-OLE to building efficient zero-knowledge protocols that can scale to handling proofs of very large and complex statements. And then tomorrow and on Wednesday, Yuval and myself will be covering the PCG part of this talk, this school on pseudorandom correlation generators in this series of 4 lectures, which will also be connected to vector-OLE, since there we will also cover some silent vector-OLE protocols, which have much lower interaction costs than this distinct kind of interaction pattern amongst the parties. So that's an extra tie in there, which will not overlap too much with what's covered today. Okay, so this talk, in a bit more detail, will start off with some basic definitions, covering OLE, vector-OLE, and a few useful variants that you often come across when looking at protocols that use these primitives, and then move on to some motivation, including multi-party computation and different kinds of applications like oblivious pseudorandom functions and private set intersection. And then finally, in the second half of the talk, I'll be looking at some basic constructions, including building OLE or vector-OLE from oblivious transfer or homomorphic encryption, and talk a little bit about how we can add active security to these protocols before wrapping up with some conclusion. Okay, so what is oblivious linear function evaluation, or oblivious linear evaluation for short? So this is a 2-party protocol between a receiver, Alice, and a sender, Bob. And Alice has some input x, which here is just an integer modulo p. You can generally define OLE over any finite field or ring, or even any kind of general finite group if you like. But here let's just focus on integers. And the goal of this protocol is to have Alice and Bob exchange a set of messages, at the end of which Alice will output this value y, which is a linear function evaluated on her input x, where the linear function is just a pair of elements a and b input by Bob. So intuitively, the security we require is that for the side of Bob, if Bob is corrupt, then he doesn't learn anything about Alice's input. And on the other side, if Alice is corrupt, she doesn't learn anything about Bob's input beyond the output of this linear function. So as is typical in secure party computation protocols, when we define security, we typically talk about an ideal functionality. So you can think of this as a kind of trusted box, which takes as input the private inputs of the 2 parties, evaluates the function, here it computes y, and just outputs it to Alice. And then when we look at the formal security definitions of 2-party and multi-party computation, then if a protocol is secure, then this definition of security guarantees that for any corrupt party in this protocol, they will not learn anything more than can be deduced by the ideal functionality, which they can interact with here by just giving their inputs and learning the desired output. So in the case of OLE, if we look at this functionality, then one kind of natural weakness, which some people find a bit odd, is that, okay, Alice can just input X to be 0, and then they learn Y equals to B. And then that seemed kind of pointless because half of Bob's input is leaked already. So of course, this is always possible. It's allowed by the functionality. But actually, in pretty much all of the applications of OLE that we look at, Bob's input B usually doesn't really matter that much. In fact, it's almost always just a random value, which is sampled independently every time you call an OLE functionality. And one way to illustrate this is a different lens of an OLE functionality, which is viewing this as secret shared multiplication. So here, Alice and Bob only have the inputs X and A, whereas Bob just samples his second input B uniformly at random. Then when Alice obtains the output Y, we can view the pair Y and minus B as an additive secret sharing of the product A times X. So now clearly Alice choosing X equals 0 doesn't help anymore because we know that this product is always going to be 0. So this case where we sample B at random is pretty much the only way that OLE is going to be used in our protocols. And in some cases, when you're building OLE, you can save a little bit of efficiency with that kind of relaxation. So I think for secure party computation especially, this is perhaps a more useful way to view and even define OLE in the lens of multiplication. Okay, so that was OLE. Let me also cover a few important variants of OLE. First off is random-OLE, where, unlike on the previous slide where Bob's B was sampled at random, here we're going to have all of the inputs, X, A, and B, sampled at random by the functionality. So there are no private inputs. The parties just receive A, X, Y, and B as outputs. And finally, we want to look at vector-OLE, or VOLE. So here, Alice still has the input X, and Bob this time has an input, a vector of elements A and B, and Alice will obtain this kind of vectorized function applied to her input X, obtaining the vector Y. And just as with OLE, for vector-OLE, we can also define a random variant where the vectors and the input X are sampled by the functionality. Okay, so building on from this, I want to show a few basic connections and observations about these functionalities. So firstly, it's kind of obvious. If you have n instances of an OLE functionality, you can use this to build a single vector-OLE of length n. So Alice just inputs the same X into each of the OLEs. So this is an unconditional, but perfectly secure reduction with passive security. And you can also make this actively secure with a little bit of work. On the other hand, if you want to go the other direction, build vector-OLE from, so build independent instances of OLE from vector-OLE, then that's kind of impossible to do with just one instance because of this restriction on Alice's input to be a single scalar. So this kind of implies that vector-OLE should in some sense be a little easier to build than OLE. And if you look at some protocols, this actually turns out to be true. And that kind of motivates focusing on vector-OLE as an important building block on its own. So secondly, if we have a random-OLE functionality, then it's known that we can easily convert this to build OLE on chosen inputs from the parties, again, with unconditional security. And here the reduction requires a small amount of interaction, where to convert the random inputs, each party essentially one-time pads encrypt their real input with the random-OLE inputs, which requires sending these 3 field elements over the network. And so again, the implication of this is that it's enough to just focus on random-OLE for applications. And in fact, in the silent category of protocols, which will be talked about tomorrow and Wednesday, that is the main goal which they achieve with much better efficiency. And finally, if we look at OLE on its own, then it's quite easy to see that this implies a 1 out of 2 Oblivious transfer protocol. So to see this, you can imagine Alice as the receiver in the OLE, also being receiver in an OT protocol, where her input X, she can now just choose to be either 0 or 1, which then kind of flips a switch, allowing her to receive one of 2 messages, which can be defined by Bob's inputs. And so because of known black box impossibility results of constructing oblivious transfer from one-way functions or one-way permutations, we kind of know that it seems very likely that public key cryptography is necessary for building OT and therefore also for OLE. So for all of the constructions we'll look at, there will be some kind of public key style techniques involved at some point in the protocol. Okay, so let's move on to some motivation for actually using OLE. Now, you may recognize this slide from one of the Let's talks yesterday. This is on secure computation in the preprocessing model, where the parties ahead of time will maybe run some interactive protocol, or perhaps obtain from a trusted dealer some source of correlated randomness, which can then be used to improve efficiency when they're doing an actual secure computation protocol after the inputs have been defined. So you have this source of correlated randomness, then the online phase can be much cheaper, information theoretic sometimes, and lightweight computation. So the way OLE and vector-OLE come in these protocols is in this preprocessing material. So we can view a random OLE as a kind of correlated randomness, which can be distributed to the parties in advance. And as a simple example here, I'll show how given two independent instances of random OLE, Alice and Bob can non-interactively convert these into a multiplication triple. So multiplication triple is used from Beaver's classic protocol for doing secure multiplication in online MPC protocols, common in all kinds of protocols. So viewing OLE as these secret sharings of the product of the inputs A and X, and the second OLE A prime times X prime, if we put these in a box to denote they're secret shared, then we can define this product of X plus A prime and X prime plus A. If we expand out all of the four cross terms here, we see that firstly, X prime is computable by Alice, and A prime is computable by Bob. And then the last two terms are exactly the secret shares, AX, A prime, X prime, which we have from the OLEs in the first place. So combining all of this together, we can use this to define a multiplication triple, where the values on the left, X plus A prime and X prime plus A, are already views as secret shares of the random OLE outputs. So this gives us this additive secret sharing of U, V, and W, where W is U times V, and U and V are otherwise random. Remember, this is a non-interactive reduction, so you just need to take the random OLEs and it can immediately define this multiplication triple with two parties. So other uses for OLE and vector-OLE in multi-party computation protocols can be, firstly, more generalized form of multiplication triples. For instance, if you use vector-OLE instead of OLE, you get this scalar vector multiplication very naturally. You can also build this up in batches to perform matrix vector multiplication or matrix triples. And secondly, if you want to go to beyond two parties, then you can have n parties run pairwise instances of OLE or vector-OLE and build up multiplication triples this way. One caveat here is that now they have to do some interaction to be able to convert the random OLE instances into multiplication triples. And there are also other approaches for generating multiplication triples based on somewhat homomorphic encryption, as used in the early iterations of the speeds protocol, which give a kind of different flavor in terms of efficiency from using OLE. And finally, one important application of vector-OLE is for building authenticated secret sharings of correlated randomness used in the preprocessing phase. So this is a key building block in actively secure protocols for MPC, such as speeds, where we authenticate secret shared values with information theoretic max. And this is something I'll also be talking about in the second talk later today on zero knowledge from vector-OLE. Okay, so I want to talk about another application briefly, which is this time just for vector-OLE, and it's for building something called an oblivious pseudorandom function. So a classic pseudorandom function is modeled by this security experiment here, where we have an adversary on the left who is interacting with some oracle, which samples a random bit B and a random key K, and then receives these queries on input X from the adversary, where the oracle will either compute a pseudorandom function F applied on input K and X, or it will sample a random function and output the random function applied to X. And the goal of the adversary is to distinguish between whether the actual function F is used or there's just the random function. And if the adversary can't distinguish, then F is a pseudorandom function. So in an Oblivious PRF, we have this two-party protocol where one party, Alice, has the key and Bob has the secret input X. And at the end of the protocol, Bob should learn the PRF evaluated on K and X, whilst not learning any other evaluations of the PRF. So intuitively, you want that the PRF applied to any other input Y not equal to X remains pseudorandom even after the execution of this protocol. So how can we build an Oblivious PRF from vector-OLE? Essentially, there's a very natural construction where you can take a vector-OLE of, say, some length n, and this will give you a batch of Oblivious PRF evaluations on n different inputs. So here, Alice, the receiver in the vector-OLE, is now going to play the role of the key holder in the OPRF. So then Bob on the right has these inputs AI, which are going to be the inputs to the pseudorandom function, and then these random inputs BI, as usual. Then Alice learns the vector-OLE outputs, and then we define a pseudorandom function as follows. So first, Alice defines a batch of keys by taking the vector-OLE outputs with this random value S and the outputs TI. Note that this is a kind of different but correlated key for each value, for each index I. And then Bob will simply define its output by taking BI, which was its random input to vector-OLE, and hashing it with some hash function, say a random oracle. Okay, so this might look a little bit strange because it's not clear that there's actually a pseudorandom function involved here. But if we take a little closer look, we can define the following PRF, which is defined by hashing, so taking a key, which is this pair S and TI, and then input AI, and hashing TI minus AI times S. So obviously this will get the same value, which Bob computes on input BI for the input AI. So this is in some sense correct. And to argue that this is also pseudorandom, so consider what happens if Bob wants to learn FKI of some A prime value, which is not equal to AI. So then this is equivalent to trying to predict TI minus A prime times S for this different A prime. And intuitively, because the secret S is uniformly sampled by Alice, then Bob shouldn't be able to guess this. And so by applying the random oracle, this will give a pseudorandom value as the output of the PRF. And actually, you don't need a random oracle for this. You can rely on some variant of correlation robustness for the hash function. But another important thing to note about the definition here is that because of the way we define these keys, which are somehow related for each distinct evaluation of the PRF, this isn't a strict OPRF. It's more it's known as a batch-related key OPRF, which is a slightly different functionality. And one more thing, so there is a bit of additional leakage strictly because Bob doesn't just learn the PRF output, it learns this pre-image BI before applying the hash function. But as I argued before, the remaining PRF outputs are still pseudorandom to Bob, so this isn't a problem. Okay, so what can we use this OPRF for? Okay, actually, one second. Yes, okay, so if we instead use a random vector-OLE to build this, where Bob takes this random value Ri, output from the functionality, instead of its input AI, then the natural way to convert this into an OPRF evaluation is to have Bob send this correction factor DI based on its input AI. This then allows Alice to adjust her keys by adding di times a secret s to define the new set of PRF keys, which again lead to the same correct outputs. And the reason we're looking at this like this on this slide right now is that if you have this, say, ideal source of random vector-OLE from some preprocessing phase, then the communication here in this protocol is just sending a single field element from Bob to Alice, which is the same length as its input, AI. So this is optimal communication for an OPRF protocol, given the random preprocessing of vector-OLE. So that's a really nice thing about this OPRF protocol when you do it in this batch way. Okay, so now let's think a bit about the applications. So one kind of different way of viewing an OPRF is that this is kind of a random 1 out of Q OT, where here Q is the field size or the size of the inputs to the vector-OLE, where Bob learns one of these and Alice can compute any of these by applying the hash function in the right way. So this is useful for certain kinds of correlated randomness in MPC protocols, like these masked one-time truth tables that can be used to perform, say, table lookups or other gates more efficiently in the online phase, as was also connected to some parts of the function secret sharing talk from a Let's talk yesterday. So another, I guess, more typical application of OPRFs is to use in things like password authenticated key exchange protocols, like the OPEG protocol. But these protocols actually typically use a DDH-based construction of an OPRF, and well, you could potentially apply some batch thing. I think for the applications they have in mind, it seems less useful to have this very large batch of OPRF evaluations, although it could be that in some cases that can be something that that works out. And then finally, I think a very interesting application of Oblivious PRF, which will be looked into in more detail in some of Benny's talks, is private set intersection. So the first uses of this type of OPRF construction for PSI were a slightly different construction based on OT extension instead of vector-OLE, and these are this KKRT paper from 2016, which reduced the use of public key cryptography in PSI protocols by relying on this OT extension preprocessing and obtaining reasonably low communication for the overall protocol. And then a more recent approach is to combine the vector-OLE-based OPRF construction with some kind of polynomial-based encoding of the set inputs from the two parties. This actually leads to a really simple PSI protocol with essentially optimal communication. So in the protocol, the two parties just have to run one instance of vector-OLE and then communicate an amount of information exactly proportional to the input size. And it's very simple and natural protocol, and it's kind of described in a slightly obfuscated way in this paper from last year from Crypto, but hopefully there's enough information to decode that and discover it if you want to learn about it yourself. Okay, so that's the main part of the applications I want to talk about. Maybe we can pause for a second in case there are any questions.
There are no questions so far. You can go ahead.
Okay, thank you. Right. So in the second half of the talk, I'm going to look at some basic constructions of vector-OLE. So as I said, these are not the silent constructions which will be covered in tomorrow's and Wednesday's talks. These are instead slightly more interactive ones. But importantly, even though these constructions are in some sense worse in terms of communication, I still think they're useful. They're important building blocks, since when you have these silent constructions based on pseudorandom correlation generators, they still require some kind of seed vector-OLEs to bootstrap them and maintain the protocol overall. So on this slide, I've got this taxonomy of, I guess, three main categories of vector-OLE protocols. The bottom are the silent ones, which are largely based on the learning parity with noise assumption. And then the two I'm going to talk about right now, which are building vector-OLE from Oblivious transfer, or building it from different types of homomorphic encryption. So there also are other approaches. For instance, you can build OLE or vector-OLE from homomorphic secret sharing, but I'm not going to discuss that today. Okay, so how to build OLE from Oblivious transfer. So this goes back to a protocol for secure two-party RSA key generation by Gilboa from 1999, which is essentially viewing OLE as a secret shared multiplication functionality, which is essentially part of what you want to compute when you generate an RSA public key. So Alice and Bob have these inputs, X, A, and B, and they want to compute AX plus B for Alice. So the first step is Alice will bit decompose her inputs into bits XI. This is a kind of natural thing when we want to do OT, where Alice is now going to play the receiver and use these as choice bits to the OT functionality. Then Bob is going to do a similar kind of decomposition for its input BI, but instead of decomposing it into bits, he's going to sample random field elements, BI, which sum up to the correct value B when multiplying by these powers of 2. So this is kind of like sampling a secret sharing of B in this special form, such that it gives the right thing. But remember here, if B is random, as it often is when we want to use OLE, then Bob can actually just sample all these BIs independently as random ZQ elements. Okay, so then the parties will run a batch of Oblivious transfers. So in the first one, Alice inputs her choice bit X1, and Bob inputs the two messages, BI and BI plus A. Sorry, B1, that should be B1 plus A. We repeat this log Q times for each of the bits of X. Bob will always input this BI and BI plus A for the same A each time. So finally, Alice will output Y, which is this sum of the YIs combined with powers of 2, the same way as before. So we look at the outputs of each of these OTs. You can see that each YI is equal to either BI or BI plus A. So this is actually BI plus A times XI for Alice's choice bit XI, which is either 0 or 1. So then looking at Alice's final output, when we sum these together, we also get that this is equal to B plus A times X. So this is a very simple and I guess quite natural way of building, doing secret shared multiplication from Oblivious transfer. Of course, if you want to extend this to build a vector-OLE, then you have to repeat this n times, where n is the length of the vector. And there are a few optimizations you can do in this case. For instance, in vector-OLE, remember Alice's input X is fixed for each of the multiplications. So that means when you translate it to the OT-based protocol, Alice's choice bits Xi are always going to be the same for each of these parallel invocations. So you can optimize the OT protocols based on that slightly and obtain some savings. So to summarize this basic protocol, it's perfectly secure, assuming we have an ideal OT functionality. And then to obtain each output of this secret shared product, we require this log Q calls to OT, where the inputs of the sender, at least, are these m-bit strings or ZQ elements. And so while if we rely on OT extension techniques, we can do this quite cheaply in terms of computation, at least, so we don't need to rely on a lot of public key crypto. This does have quite high communication costs. So we do m of these OTs on m-bit strings, so that's already at least m squared bits just for communicating the inputs, on top of whatever else we need to do the OT. This is essentially a quadratic blowup in the field size for doing a single OLE. Then another thing I want to talk about is active security. So what happens if we have active adversaries in this protocol who might misbehave and do something different? So firstly, if we look at the case when Alice is corrupt, note that all she's doing is inputting these bits Xi into OT. So if she inputs a different bit into OT, as long as the OT protocol is actively secure, This is just changing an input. It's an input substitution. This is perfectly allowed by the ideal model with active security, so that's not a problem. The more challenging case is when Bob is corrupted. So here, remember, Bob's supposed to input this fixed difference, bi plus a, into the ith OT. And what happens if Bob uses some a prime in one of these executions? So here, if we do it in the first OT, then the output by Alice at the end when computing y will have this additive error, depending on the difference a prime minus a multiplied with the bit x1. So this is something we have to try to prevent and make sure that Bob can't cheat by inputting different values and breaking correctness. So one natural thing we might want to try is just do some correctness check on the outputs of the OLE, or vector-OLE in this case. So this is, I guess, kind of following the spirit of Henry's talk yesterday about secure sketches for verifying properties on secret shared data. I think whenever you want to build an actively secure protocol, one of the first things to try to think about is, well, firstly, looking at what goes wrong when the parties are corrupted. And secondly, just seeing if there's some cheap way of verifying correctness without having to throw on expensive techniques like zero-knowledge proofs and things on top of that. So in this case, we just want to check that if we have a vector-OLE, then all of these outputs satisfy this relation. Yi is AIX plus BI. A simple way to do this is have Alice send some random challenges over to Bob, so random field elements, and then Bob will use these to define some linear combinations of its inputs AI and BI, and send back this response A star, B star over to Alice. Alice can then define the corresponding linear combination to the sum of the challenges times by her yi's, and then check that the OLE relation holds on these linearly combined values. So because OLEs are linear and we're just taking linear combinations, we get the same relation on the final outputs. Y star is A star times X plus B star. So there's one kind of obvious problem with this approach, which is when Bob's sending these A star and B star values, this is implicitly revealing some extra information about Bob's inputs. This is revealing a public linear function on the inputs, and we can't be having that. So we have to tweak this slightly by adding an extra mask to A star and B star. So we can do this by just extending the length of the original vector-OLE to n+1 and padding these as we go along. And Alice will add the same padding to Y star before doing the check, and that should fix this problem. So intuitively, the reason why this check should hopefully guarantee correctness is that to pass the check when some value yi was incorrect, because, say, Bob cheated in the protocol, then Bob has to essentially predict what the corresponding random challenge was in advance so that it will be canceled out by the right thing during this check. And the intuition here is that when these random challenges are chosen from a large enough field, this will succeed on with probability 1 over the field size. However, for this case, this unfortunately doesn't quite get us what we want. And the reason goes back to the exact kinds of errors that Bob can introduce on when he inputs some inconsistent input to the OT. So remember, we have this additive error, A prime minus A times X1. Of course, this error actually depends on Alice's secret input, X1. So if X1 is 0, then there'll be no error. And otherwise, there'll be this error chosen by Bob, essentially. So this is exactly a selective failure attack, which means that just based on the result of whether the correctness check passes or not, the corrupt Bob can learn 1 bit of Alice's input. This is something we may want to deal with. So one solution is actually just to not deal with this, relax the vector-OLE functionality by allowing a small amount of leakage on the input X from Alice. So you can kind of model this by allowing the corrupt Bob to choose some guesses on X. And if the guess is successful, Bob learns this fact And if the guess is incorrect, then the protocol will abort. So this is essentially, on average, kind of 1-bit leakage on Alice's X. And it turns out for a lot of applications, this doesn't really matter, and you can just proceed with this small amount of leakage. And if you do want to get rid of it, if, for instance, X is protecting something really sensitive, then you can do some kind of privacy amplification by repeating the protocol a few times and then randomly combining different instances to ensure there's enough entropy in these X values, even after a bit of leakage. And this was something used in the Mascot protocol for generating multiplication triples using Oblivious transfer. So I should say that in Mascot, at least in KOS 16, they're not explicitly building either OLE or vector-OLE. They're directly building multi-party multiplication triples, but the techniques in there are kind of implicitly building OLEs on the way. And if you want to pull that out and use it to define a separate OLE protocol, then you could do. Okay, so to summarize, if we just want the passively secure protocol for vector-OLE or OLE, then we have this very simple protocol with lightweight computation if we make use of fast OT extension techniques, with this main drawback that the communication cost is now quadratic in the field length, which can introduce a lot of overhead in certain applications. And for the case of vector-OLE, at least we can get active security very cheaply by doing this simple linear combination check. And if we tolerate a small amount of leakage on Alice's input, we don't need anything more, and it's essentially active security for free. So that's very nice. It's a simple protocol, and if you don't care about a bit of extra communication, it should be enough for your needs. Okay, so a different approach is to build vector-OLE from homomorphic encryption. This will have different trade-offs to the OT-based approach. The main goal here, I guess, is to reduce the amount of communication and avoid this quadratic overhead. So here we're going to use a linearly homomorphic encryption, which operates over vectors of messages. So we have a public key encryption scheme with the usual algorithms, where the plaintext space is now vectors over ZP. We want this linear homomorphic property, where given some ciphertext, okay, so here I'll be using this box notation for encrypted messages. So given some ciphertext encrypting a message A and a ciphertext encrypting message B, we can add these two things together homomorphically. We can also multiply by a constant. When we multiply by a constant, this could be a scalar or it could be a vector over ZP. And in the case of it being a vector, we now do component-wise multiplication of C times A after we decrypt, so that we get the right thing with this SIMD style operation on encrypted vectors. So how can you build this kind of homomorphic encryption? Well, there are many different ways of building homomorphic encryption. A classic approach is the Palier encryption scheme, which doesn't actually encrypt vectors, it just encrypts scalars, but you can always just encrypt one element at a time to get a vector homomorphic encryption scheme. But the main drawback of Palier is that the plaintext space is now this ring Z modulo n, where n is an RSA modulus, so which obviously has to be very large and maybe a bit restrictive for your application. There'll be more about Palier and related techniques for building vector-OLE from this in my talk on Wednesday. So another way of building homomorphic encryption might be to use the DDH assumption, the decisional Diffie-Hellman. So if you use classic Elgamal encryption, where you encrypt the message in the exponent of G, and then this becomes additively homomorphic. The only catch is that now to be able to decrypt, you have to solve the discrete logarithm problem. So this only works if your plaintext space has polynomial size. One nice way to resolve this issue is to work with class groups, where you can then support plaintext modulo P for large primes P. But finally, the actual main example I have in mind for this talk is using a lattice-based encryption scheme. So most efficient schemes from lattices are typically based on the ring learning with errors assumption over polynomial rings, where these schemes actually natively encrypt vectors expressed as polynomials. So we can directly encrypt a vector over ZP and do this component-wise addition and multiplication in a batch on a single ciphertext. Okay, so we can very naively build vector-OLE from linearly homomorphic encryption by just having Alice take as input X, which is the scalar in ZP, encrypting it, and sending over the ciphertext and public key to Bob. So yeah, if the encryption scheme operates on vectors, you can just imagine Alice packing X into every component of the vector in the same way. So Bob will just apply this linear function based on his vectors A and B to compute a new ciphertext and send this back to Alice, who decrypts the result. Okay, so this is all very simple. It's a classic protocol. But I think it's helpful to think about what it actually takes for this protocol to be secure. So kind of obviously from Alice's side, if Bob is corrupt, then we want this encryption scheme to be secure. So if we have CPA security, then the encryption of X should hide X. And secondly, on Bob's side, if Alice is corrupt, we want the ciphertext Y to completely hide Bob's inputs A and B. And this actually isn't guaranteed by CPA security. This is a stronger property called circuit privacy, which says that after doing some homomorphic evaluation on a ciphertext, if I know the secret key and I've seen the ciphertext, then I cannot distinguish the actual function which was applied on the original ciphertext. So we have this property, then we get a secure protocol for a corrupt Bob. But unfortunately, when we're using lattice-based encryption schemes, circuit privacy is a bit of a problem. So for instance, in ring LWE-based encryption, we often have this like noisy structure of a ciphertext, where in your ciphertext, so firstly you have to scramble by masking with some function of the secret key. But if you take that away, then what you have is the message, which is encoded in, say, the upper bits of the ciphertext, and then it's partially hidden by some noise component of the ciphertext, which is in the lower order parts of the ciphertext, which are some integers modulo q. So now when we apply a linear function to a ciphertext, the way we do this homomorphism is essentially applying the same linear function on the ciphertext elements as you would on the plaintext. We now get this different noise term, which depends on the secret inputs A and B chosen by Bob. So when Alice decrypts the ciphertext and recovers the noise to remove it, she will then have this leakage on the inputs A and B, which we want to hide. And the classic solution to this is to do something called noise flooding or noise drowning, where when Bob computes this linear function, he'll sample a large amount of extra noise, add this to the ciphertext before sending it over. But if we want this to statistically mask the original noise, A times E plus B, then we need this extra noise sampled by Bob to be really, really big. It has to be essentially 2 to the security parameter times larger than the original noise in the ciphertext. So doing this requires larger ciphertext parameters. It increases the parameters of your lattice-based encryption scheme and makes everything much, much worse. So I want to mention there's a really nice technique which was presented by Vinod Vaikunthanathan at a workshop as part of crypto last year. There is a video online where you can remove this noise flooding using something called gentle noise flooding, where instead of adding a very, very large amount of noise, you add just a small amount of noise and then essentially allow a small amount of leakage on some of these coordinates in the ciphertext. The way you work around that is then instead of encrypting the original message, you'll encrypt a T out of N secret sharing of the message. So that when Alice decrypts, if by some chance when this noise doesn't map things properly, she learns a few coordinates of the original messages, then because these messages are just secret shares, it doesn't matter as long as she doesn't learn too many. So that's a nice technique for working around this, which allows you to work with much smaller ciphertexts and reduce the bandwidth and computation overheads from the naive method. Okay, so the second thing I want to talk about for linearly homomorphic encryption is how we can add active security to this. So again, it's instructive to think about what can go wrong. Is there some obvious attack that can break things? Well, in this case, not really. I mean, you can always have Alice and Bob send some kind of garbage ciphertext and then violate correctness, but it's actually quite hard to figure out how to do this in some way that leads to some leakage of sensitive information. Of course, that doesn't mean that nothing can actually go wrong. So we can try to say, okay, let's run this nice linear correctness check we use for vector-OLE in the OT-based protocol and try to just verify things are correct. It's not obvious that there's any kind of selective failure attack, but we do get some kind of weird error in the outputs that has some dependence on the ciphertext noise, potentially the secret key used in the encryption scheme, and can cause things to fail in strange ways that are kind of hard to analyze. So it would be really nice to show that, okay, if we just do this, then we're all fine, there's no problems. But it's kind of challenging to prove that this was enough. So the way we actually add active security to these protocols is to go to the slightly less satisfying solution where we add zero-knowledge proofs. So for Alice, we want to prove that the ciphertext is correctly well-formed, which is a kind of proof of plaintext knowledge. And this guarantees that in the simulation, then the simulator can also extract the plaintext, which is needed for malicious security. And then for Bob, we want to prove that Bob applies this multiplication function to the ciphertext in the correct way. So this is for a zero-knowledge proof of correct multiplication. And doing these proofs for lattice-based encryption schemes is unfortunately kind of tricky, essentially because of the noise, which you don't have in classic number theoretic assumptions. You have to work a bit harder. So for the proof of plaintext knowledge, there's a very simple and naive Sigma protocol with just a 1-bit challenge. So just get soundness a half, which then you have to repeat security parameter times, which obviously is undesirable. But there are many papers that look at optimizations to this approach. You can have slightly larger challenge spaces. You can amortize it when we want to prove knowledge of a large batch of ciphertext at once. But all of these are still kind of computationally expensive. They sometimes need larger parameters or only work on very large batches of vector-OLE instances and add quite a bit of overhead compared with just a simple passive protocol. And then things are actually even worse when you look at this proof of correct multiplication. This is much harder to amortize compared with the proof of plaintext knowledge and adds a lot of overhead there. However, there is this nice technique from the Overdrive paper used for triple generation for the speeds protocol, which essentially uses a kind of vector-OLE-like protocol, somewhat similar to what I described, where we have a proof of plaintext knowledge, but it just then does some lightweight consistency check instead of adding these proofs of correct multiplication. And this can be proven secure if you add some extra assumption, which is sometimes called linear-only encryption, which is saying that essentially the only thing a corrupt Bob can do when it sends back a ciphertext to Alice is apply some linear function to the ciphertext or send some garbage ciphertext, which will always decrypt to an invalid plaintext, which is either invalid or independent of the original message. And this is kind of a strong assumption. It's been used in some lattice-based snark constructions, but it seems to be plausible. So there's one way of making things more efficient. Okay, so that's coming to the end of what I wanted to present for OLE and vector-OLE. So I'll just conclude a little. So have you seen these two things are kind of core building blocks in all kinds of secure computation tasks. We can use them to generate correlated randomness of many different forms, multiplication triples for matrix triples, as well as more special purpose applications like Oblivious pseudorandom functions, which are a really important building block for private set intersection. The next talk will look into much more detail on a specific application to efficient zero-knowledge protocols from vector-OLE. And we looked at these non-silent protocols, so the classic protocols based on Oblivious transfer and linearly homomorphic encryption. And even if these silent protocols, which we'll talk about in the coming days, are in many cases faster and perhaps preferable, I think the non-silent ones are still actually very important. Firstly, they're based on different assumptions, which may be more standard. And secondly, as I mentioned, these silent protocols always need some kind of setup phase to bootstrap them and obtain the silent benefits, which obviously has to be done with some kind of interactive protocol where we need this base OLE or vector-OLE primitive. So it's still an important building block to look at, and there's still a few open questions, especially when it comes to doing active security with ring LWE-based encryption schemes. These zero-knowledge proofs are kind of a bottleneck and would be really nice to either improve or avoid. Okay, so that's about all I wanted to cover. So I'll be happy to take any questions if there's anything on Slack.
Yes, there are a few questions. So the first one is when you refer to silent OLEs, what does silent mean here?
Yes, so I guess I didn't really explain that. It'll be covered more tomorrow, but silent essentially means that you have this interactive setup protocol which has very small amount of communication and just outputs a small kind of seed, which can then be non-interactively expanded to produce a large quantity of vector-OLEs or OLEs. So it's split into two phases, this kind of small interaction phase and then this silent expansion into a large amount of correlated randomness.
Okay. Also, when you do the jungle flooding, what's the advantage of using T out of N sharing instead of using just using an N out of N sharing?
Right. So I think for that one, it's not my work, but you need to use a kind of T out of N for some less than full threshold T, because you need to be able to, you kind of tolerate up to N minus T leaked coordinates in the ciphertext. And intuitively, each coordinate might leak with some constant probability, say probability of half, which means in the worst case, like up to half of these coordinates might be leaked. But I know, but then you need a smaller threshold so you can also reconstruct the original message, despite this leakage.
And then with respect to applications, there's a question if we can use vector-OLEs to construct protocols that can obliviously return shares of a value that is computed in a distributed way in the multi-party setting.
Okay, so I'm not sure I entirely follow the question, but is it perhaps talking about a kind of distributed secret shared version of vector-OLE?
I think so. So the question says that it is in the multi-party setting with more than a single receiver where the values are computed distributedly and you want to obliviously return the shares.
Yes, okay. So imagining it's like a vector-OLE where all of the, say, instead of X known to a single receiver, it's distributed across multiple receivers. And you have these kind of secret shared outputs of the vector-OLE. So that's what you're looking at, then yes, that's something you can build, essentially from pairwise instances of vector-OLE across the parties.
Okay. And the last question is the overdrive technique, the random linear combination check, an alternative to zero knowledge in RLWE?
So that's a good question. I don't know. It seems like you probably need something more. If you do just this check, I think it's very hard to actually prove that the ciphertext was well formed in the first place. But this kind of check is essentially very similar to the zero knowledge proofs that happen already. It's just they have to essentially do some more work to be able to prove things are well formed and extract the inputs. But it could be that something very close to this can work out.
That's all of the questions we have.
Great. Thanks very much.
Thank you very much, Peter. We're going to take a break, a lunch break till 2 o'clock. Resume then with your second talk for today. Thank you very much, everyone.